So basically, let me quickly summarize what we have learned so far, right? So if we want to apply spectral graph partitioning to find two clusters in a given graph, there are 3 steps we have to go through. In the first step, we have to do what is called pre-processing, where we construct a matrix representation of a graph. In the second step, we go and compute the eigenvalue decomposition of this graph by identifying eigenvalues and eigenvectors. In particular, we are interested in the second smallest eigenvalue, lambda 2, and the corresponding eigenvector x. And then, once we have the vector x, all we have to do is we have to go and do the grouping, where we basically look at the components of x and determine which nodes belong to the set A and which nodes belong to the set B, right? Kind of who belongs to the left partition, who belongs to the right partition. So let me now give you an example, right? So in the pre-processing step, I take our graph G and compute the Laplacian matrix L. In the second step, then we do the eigenvalue decomposition, where basically we take our L when we find a set of eigenvalues and a set of eigenvectors to this matrix L. We take the second smallest eigenvalue and the corresponding eigenvector. Here it is, right? We take this one out. So here are now all the nodes 1 to 6, and these are the corresponding entries of the eigenvector. And what we find, for example, is that now what we have to do is we have to group these nodes, right? We would like to group these nodes into 2 clusters corresponding to the embedding or the labels of the nodes that we have in the corresponding eigenvector. So how do we do this grouping? Doing the grouping is very simple. We basically go and sort the components of vector x and identify clusters by splitting the vector in 2. So a naive approach to this case would be to ask, what are the corresponding values that are negative? What are the corresponding values that are positive, right? So if this is our vector x, we would split it here between nodes 3 and 4. These are all the nodes that are on the right-hand side of the 0. These are all the nodes on the left-hand side of the 0. Notice that sum of the node labels equals to 0, exactly as we said it should be. Also notice the sum of the squares of the values equals to 1, which is again exactly as it should be. So what this basically means is now by splitting this vector in half into kind of the positive part and the negative part, we identified the 2 clusters. Here is the cluster A, which is composed of nodes 1 to 3, and the cluster B that is composed of nodes 4, 5, and 6. So I have an A and I have a B, right? So basically, what the components of second smallest eigenvector did, it basically embedded the nodes on a line, assigned them positive and negative values. We take all the positive nodes, put them into cluster A, take all the negative nodes, nodes with negative values, put them in the cluster B. So now, if I give you a bit more interesting example, here I have graph on the left G that you see it has 2 clusters. I computed the graph Laplacian, I computed the lambda 2 and the corresponding eigenvector x, and all I did here is now I sorted the vector x2, right, the corresponding eigenvector to the second smallest eigenvalue by the entries. And what you see very nicely is there is a set of components that has a negative value and a set of components that has a positive value. So basically, the eigenvalues or the entries of the eigenvector with a positive value correspond to one cluster, and the remaining ones correspond to the second cluster. Of course, you can now start asking, is there anything interesting about the eigenvectors that correspond to, let's say, the third smallest eigenvalue, the fourth smallest eigenvalue, and so on? And just to, for example, show you what happens that, the first case I'll show you is a graph that I have here that actually contains 4 small clusters. If the graph contains 4 small clusters and I still compute lambda 2 and the corresponding eigenvector x2, what I show you here is now the components of this eigenvector. And you see how the entries now first are split into 2 clusters, right, kind of above 0 and below 0. But then you actually find that here we have these different steps, right? So basically, we have first the 2 clusters, and then each of the 2 clusters has 2 small clusters embedded in them. And we see this kind of from the structure of the components of the second eigenvector very nicely. So the question is, if I have multiple clusters, how would I go identify them? So let me just show you some examples how to do this. For example, if this is my graph G, the same as I had before, I have my Laplacian matrix L that I do eigendecomposition. For example, here are the components of vector x1, and they all have exactly the same value, so exactly as we said and as we have proven. But for example, the components of the third smallest eigenvector are the following. And now what you see here is, for example, that this is the bottom cluster, this is the second cluster, then this will be the third cluster, and here these components correspond to the fourth cluster. So basically, what does this mean? This gives us now an idea of how do we go if we want to partition a graph not in two clusters, but in k of them. There are two possible approaches. One approach is to do recursive bipartitioning. It's basically take the full graph, split it in two, and now for each of the two pieces, again, kind of try to split it in two. And we keep applying this recursively until we are getting kind of smaller and smaller pieces. And another idea is to basically cluster using multiple eigenvalues and multiple eigenvectors. So basically, the idea is that for every node in the graph, we take our Laplacian matrix, compute the eigenvalue decomposition, and now we take the second eigenvector, the third eigenvector, fourth eigenvector, which basically means that every node of the graph is now described by a small vector of values, and now we can apply k-means or something like that to identify the clusters. So basically, the idea would be that we take the graph, compute the Laplacian matrix. From Laplacian matrix, what we will do is for every node I, we will come up with its corresponding, in some sense, coordinates, right? So we will take the coordinate I of second smallest eigenvector, coordinate I of the third smallest eigenvector, and so on and so forth. And now that every node is described by a set of coordinates, we can run k-means that we have already discussed how to use to identify k clusters. And it turns out that in practice, this method works really well. So with this, we have finished the discussion of spectral clustering and basically given a graph how to find individual clusters of nodes in it.